My name is Joseph Wunderlich. I'm a professor of engineering, architecture, and computer science. This is approximately 2.5-hour lecture. I'm going to compress the narrative down to a much shorter time. Students should take at least 2.5 hours to go through this material, preferably 4. I like this particular lecture because it somewhat merges my 5-year architectural engineering education at the University of Texas, Austin, and Penn State, 2 years urban design, and University of California, San Diego, and then architectural work until age 30, plus my master's and PhD in electrical and computer engineering after that. And so it's a merging of those two worlds for me. The main reference sources here will be our this textbook that we're using on heating, cooling, and lighting, and also the Illumination Engineering Society handbook, as well as a number of other sources. So firstly, we always want to make maximum use of the sun, the natural lighting. Passive, you always want to do passive things first before active. And these are some photos from Rome that I took in 2011. So we want to speak of daylighting first. First go back, students, and just take a quick look at Chapter 7, the HVAC passive solar heating, and also the Roman architectural and engineering. We've already spoken about some of this history, so I'll go quickly through this. Until the 1800s, no artificial lighting during the day, and so going back in history now in Western civilization, we see what the Romans did, some of the ways they first started bringing in light with and the structure, the flying buttress on the cathedrals allowed for the more openness, as opposed to a huge, thick exterior structural wall. You could go up now and open up. In the Renaissance, the windows started to dominate walls. And then pre-1900s, we see floor plans in the United States and elsewhere that are these different shapes. You see the H, O, U, and W here. And they allow to have maximum light and, importantly, although not discussed so much in this lecture, really good ventilation too. I'm recording this right in the middle of the COVID pandemic, actually in November. So something to think about as architectural designers for future. Industrial revolution in the 1800s, and modernism 1900s. So we have now curtain walls of glass, mass production of things, skylights, huge sun spaces, glass block. Our technology allows us to open things up. However, in Asia for thousands of years, sun was integrated into the way of life. So, we just mentioned Western civilization, now non-Western. So Japanese, or Chinese first, 6,000 years old. I'm not going to go through all the details here. It's somewhat of a spiritual belief, if you will, or a philosophical belief in some of the things that manifest itself based on how you deal with the sunlight. So you can read through these different things, how to orient the house and the windows, and where to put the rooms. Then in Japan, more recently now, this is a stepped mountain home, which makes use of light as well as wind, water, and shadows. And you can see how the sunlight's coming in here naturally, different floors, different ways. You can imagine different times of day. This is a project of mine 30 years ago, opening up this building, this house. I put these skylights in facing the southern. There was only the southern view. There was only window on the north and west side, and the west side was blocked because of a house up on a hill next door. So this really opened up the natural lighting in here. Otherwise, it was always lit with artificial lighting. There's an exterior view of that same project. Now, throughout time, it's not a new thing that we're worried about the sun. In the Roman times, they had sun rights, actually laws for that. In England in 1200 AD, daylight access laws, 1900s, New York City zoning, and then presently there's many rules, regulations, zoning laws, building ordinances, mostly the zoning, restricting sunlight from adjacent properties from being blocked. Now, some details here. So, LEED credits. We're speaking of leadership in environmental or in energy and environmental design certifications for buildings to get platinum, gold, silver. You get 1 credit for 75% of the building being with natural daylight, 2 if 90%. 1 to 10 for daylight improving energy efficiency. So that's a double effect. So you always want to think about the thermal effects. Sometimes it's contradictory to the daylighting effects, but sometimes it's beneficial, equally beneficial. And then 1 for 9% of occupants having good views. Views also, right? You must think of the psychology of the people working and reward that, and LEED does. Reflectance, the way you channel light in. You want to get it into the building, and you can do that in different ways with different materials around the perimeter, even sidewalks outside, white gravel in front of the windows. There's ways of reflecting the light into the space. So we have a daylight factor now. This is the percentage, it's a ratio of the illumination getting indoors to the sun outdoors. And this table's on an overcast day. So this is going to be drastically different. And by latitude or region where you are, if it's a bright sunny day in Arizona versus in typically areas with more humidity, and even when it's sunny and more diffusion of light, you're going to get different things. So this is a baseline standard using an overcast day, and then you change based on where you are. So the basic idea is for studios 4 to 6%, 2% offices, lobbies 1, hallways, bedrooms less 1.5%, and of course varies by floor plans. So you need to take extra measures to channel the light in the building, or you're going to have artificial lighting, which you will in most cases, but optimally you could get away with just natural lighting during a large percentage of the time. And then you also want to consider, very importantly, there's a lot of balanced trade-offs of cost and benefits of this light to solar gain ratio. So now you're considering the heat from the sun that you're getting. And that's a cost if you don't want it. You may be wanting to heat up the house. It depends what time of year. So it's something you want to consider. And again, this is going to vary by location as well as time of the year, what you actually want as a goal. So you think about this a little bit. It's not just a this or that yes or no kind of thing. So you see different ratios for clear glass, reflective glass, and low E glass, where you let most of the light in but block most of the heat. So this is something did quite a bit in buildings in the West and California and Texas with things that I was participating in building. Now, students recalling Chapter 9:10, passive cooling and shading, we already took a look at some properties of glass, including the solar heat gain coefficient and shading coefficients. And we spoke of reflective glass that I worked with in Texas and California. As you can see in these projects below, nowadays these are also typically low E. Now our daylighting factor, you can assign feelings of how people will feel, the atmosphere, the ambiance. So that the daylighting factor below 2% is gloomy feeling. 2 to 5%, you feel like it's well lit or it is daylit, and then above that, you feel it's vigorously daylit. Now there's illumination gradient that we've mentioned before, directing, reflecting to get the sun indoors. And then also the building orientations, which we've talked about before in a couple places. So recall in chapters 5 and 11, in site design, orienting south, north, east, and west for different things that we're considering, design considerations, also skylights, and if the sun's too intense, you might want to put blinds on them also, which I end up doing on that one project I already mentioned. And you can see more on those kind of things with shading in previous lecture in Chapter 9:10, passive cooling and shading. Now, how to get the sun deep into the building, a nice list here from the text on heating, cooling, and lighting. And these shapes that we mentioned before that we may want to bring back now to let more daylight in and have operable windows for ventilation, especially during pandemics. And then we have the envelope-dominated building designation for that kind of thing, as opposed to internally dominated, so that we'll abbreviate this from now on. The textbook does that, and you'll see it in other places, the ED and ID. Internally dominated, you need to get lights in other ways. Clear story skylights, curtain walls, and light scoops. Also, tall ceilings, tall windows, distribute windows evenly. Light-colored walls, channeling it in. Translucent drapes, channel light with operable louvers. We saw that on one building. Previous lectures. Channel light in with reflective window sills. Glass floors, that could be a little problematic, but heliostat is this technology thing you can do. Actually scoop the sun, collecting it, channeling it in with fiber optics. Translucent walls and windows. This is one in Pennsylvania, Lancaster, Pennsylvania, Park City Mall. It's a huge tent in the main center of the wagon wheel floor plan footprint of the building. Central location. Not where the food zoo is, though, oddly enough. I think that would cause a little too much congestion. There's a couple food things, but the main food zoo's down one of these spokes of the wagon wheel, down below. Now, we want to speak of mixing natural light and artificial light, and most importantly, how we people feel about it. So, we're designing architecture is for buildings. Engineering, too, for people, is for people. So spatial orientation, where you are in time and space. Well, space, not time, but also time is number two. Form identification, edge detection, where you are, where your edges, where your boundaries are. Activity enhancement can enhance your work productivity and enjoyment. Define a personal space. You feel nice and safe, and you have your own territory. Happiness. Overall, we need daylight, real or simulated. You can do it with some artificial light, which we'll see actually in this lecture. It's not easy to do. Getting nice even distribution of all the different wavelengths of light that make up natural sunlight. Visual diversity needs. Right. We need a little bit of change. Order needs. A little different for different things for different people. Security, well lit for safety certainly. Light poetry, so this is more artistic thought here. So sunsets, sunrises, sunlight on a stream, fountains, waterfalls, koi ponds. Light on water can be very desirable thing to do. Uplighting on statues and buildings and trees. I like to do that with the trees around my house. Spots on paintings, halogen lights are the lights that really bring out the color rendering of the art. Combine source types with wall, ceiling, floor colors and textures. So different types of fixtures and different locations and for different purposes. We'll talk about that a little more here coming up. Maximum natural daylight, of course. Now, we want to look at now some specific things. So this is something I got convinced the library to buy. It was very expensive. I think they got a little bit of a discount, but it was about $500 and over 1,000 pages. It's on reserve still, or you can get it in the library. And I was teaching as part of architectural studios that I teach. I rotate 4 different types of lecture series, so whenever you take one of the studios, you don't get the same thing. But this was on lighting, and so you see here next a case study on galleries. So this is for the artwork. You want to focus on the artwork, not the people. You want to use northern sunlight for soft light, free of glare. Goes for all studios typically. Don't allow direct sunlight on the art. It can damage things. Daylight first, and then highlight art as needed, only if needed. Control magnitude of the spectrum, the intensity, distribution of the energies to prevent damage. So you want to really consider that. Your art conservators can tell you more about that when you're designing the space. Thermal effects of the light, right? You want to heat it up. Identify high, low, or no sensitivity art. So you light accordingly, or exhibit accordingly. Only use subtle or soft accent lighting. Not on art, but for wayfinding and highlighting architecture. Minimize impact from adjacent high luminance spaces. So you've got hallways and bathrooms, sometimes food areas. So you might want to light lock, like you see in theaters, between the space, the art exhibit space, and if it's a big museum or art gallery. You want low reflectance everywhere in the activity spaces and the art space, exhibition space. You want indirect lighting to enhance ambient light and find wayfinding and highlight architecture. Use wall sconces. That's like little seashell things you can see on the walls. Sometimes they're conical kind of things with the light shining up or down. Pendants hanging down, chandeliers, uplighting, different ways of doing that. So here are some photos that I found off the internet of different things. Some of these are things I've actually experienced. I've been to Venice 4 times, and it's one of my favorite places to go. Once was at the Biennale. It's a big world international art exhibit all over Venice. This is from a picture from 2013 off of the internet. Here's somebody doing a project to resize a room, mixing natural and artificial light. Using those design criteria. Maybe they didn't have the design book with them, but they certainly seem to be adhering to the rules. Here's another one. Some of these I have visited. I recall this one here and this one here. And I believe, yeah, I was in here too. Yes. I don't believe I saw this one. Pretty sure I didn't. But it gives me something else, another reason to go back. You could live in Venice and probably not see everything there is to see in a lifetime, maybe. I know I was in this one, yes. So now this is another source, a collection of slides here from this source, and you can go there and take a look at them. I didn't edit these in any way. This is just some really nice things to think about. So firstly, natural light, which we've been talking about. What path does your eye take through the room? Effect of color and lighting. Wall paint colors. Definitely has an effect on the lighting. Colored light, whether you color the lens itself or it's a pigment in the mixing of the glass or a diffuser, or different ways to make the light colored. LEDs via the technology internally. Color and emotion. How would you describe the color red? Right, and this varies by person, but you could generalize somewhat for most people. Color and emotion. Is blue a bus? Where does it take you? More color and emotion. How would you bring in a breath of fresh air without opening a window? I could feel that. Certainly the ocean. If yellow's a song, what are the words? Timeless color trends, right? So If you lived through the 1980s, it was all pastel, especially in the Southwest, Texas, California, everywhere. And then, of course, in the 70s, gaudy primary colors, sometimes conflicting. And then I would think somewhat subdued in recent times, but there's trends. So, you want to have somewhat timeless architecture if you can help it. Now here's a couple other slides from another source. This is more of an engineering / architectural still, but this is getting more specific about engineering kind of thing. So distinct contrast between individual zones and their surrounding. And so you can do that with light. I won't read all these things, but you can vertical separations. Come back, and students, again, this should be several hours lecture, at least 2, probably 3 would be best. We'll finish this much quicker than that right now. So do come back and look at this, how you make vertical separations with light, horizontal separations with light. Examples of that. Emphasizing architectural features with your lighting, layout and pattern clarity, relationships of spaces, adjacencies between spaces and parts within the space, functionality, of course, task lighting. That's a very specific engineering, illumination engineering kind of thing to get that right. And there are actually codes for that enforcement in some places. This is a case study of a theater design. I won't go through all the details here, but you can see this is, I think I just have this one slide, but you can imagine that's a very important thing to do right where we are here in central Pennsylvania, Elizabethtown, Pennsylvania. We're making this nearby Tate Towers and Clare Brothers and the Rock Lidditz. Tate Towers is a former band manager for Yes, and the Clare Brothers are 2 engineers, I believe, from Millersville. They were acoustical engineers, did audio things. A huge concert production. People fly in, all kinds of artists from Taylor Swift and John Mayer recently. Flying a helicopter. There's all kinds of things going with it. So that's something nearby for people to think about. Now, of course, during COVID, which we're in the middle of now, I'm recording this November 2nd, 1st of 2020, this production is not so big. Architectural lighting now. Take the time, students, in class, we might even take and listen to this and comment while we're going in lecture time. I forget the exact time of this, but do listen to this. This is a very good thing on lighting strategies, tips, and also lighting at nighttime. Another video, watch both those. Now, colored temperature, when you're specifying or picking light bulbs to go in your fixtures, you speak of warm, cool, and daylight, and then there's a temperature rating in Kelvin, right? Fahrenheit and Celsius, probably Kelvin's another temperature scale. You can look at the conversion for that, but this is how it's typically rated, and you can see the effects and the appearance and the ambience and what it is best for each of them. Another graph showing some more details of that. And more details of that, giving an idea of how relative temperature in Kelvin makes a difference. Also comparing color temperature with noon sunlight to the different types of fixtures that we're going to look at. The LEDs, and there's a laser in there too, tungsten filament, fluorescence. Now we want to speak about the color rendering index. This is very important to what you see and how things actually appear, and it's on a scale of 0 to 100. And daylight, of course, is going to give us the most appropriate for the way our eyes work, since we've adapted to sunlight as living beings on this planet. Before we get into the color rendering index, though, we should learn a little bit about additive and subtractive color. So to learn about additive and subtractive color, we want to look, this is an excerpt from a lecture I have in a high-tech class on color physics and displays, computer monitors. And so again, we're looking at the visible range of wavelengths that we see of the electromagnetic spectrum, and it's broken down into primarily a red, green, and blue range. There's a color wheel that we use in both technology and in art and architecture, and you can see how that lends itself to RGB values in a second. So the RGB values look like this in the mixing, and the main difference we're going to see here in additive and subtractive color is that light, as a wave going through space, the wavelengths of light, the different frequencies, wavelengths that correspond to the different colors in the visible spectrum will mix to make white light, and that is an additive process. And it's also the way the monitors work, because it's essentially shooting, or there's different types of technology, the CRT and a plasma and a liquid crystal display, but essentially there's a stream of photons of effective mass photons, waves coming at you based on excited atoms from the technology, and they're mixing. Now subtractive color is a different thing. That is a function of reflectance. So when you look at a red apple, what you're seeing is the only color that's not being absorbed. And so that's how computer printers work. You can read about this later and a little more here and understand how the printing works in computer printers, because it's a reflective thing that you're looking at. So the ink, you have to have the ink work such that it's a subtractive color process. And then a little more here, you can look into the RGB values if you're interested. Now back to architectural color rendering. So we want to pick certain fixtures, specify fixtures for our clients as architects and engineers. And so this is the how the power distribution, spectral distribution for fluorescence lights work. And this is a warm white. You see it peaking in the red. And then cool white peaks in the blue. Now you can buy daylighting bulbs, a little more expensive, that will give you natural daylight fluorescent bulbs. I've bought those even in the 80s, and then it's more like sunlight. I don't care for the wavelengths of or the fluorescent lighting myself, both color rendering and the flicker, and it's not true sunlight. So here's what the color rendering index will do for you. You can see 100 on the left, and then a lower 170 on the right, all with the same 2700 Kelvin temperature lighting source. You need to specify that as well. This is a comparison of different types of bulbs. You see on the far left, incandescent does represent the most closely to sunlight, as well as halogen. So it's very nice for artwork. And then on the far right, the low pressure sodium, and you'll see huge auditoriums, or like gymnasiums, filled with this sometimes for the light distribution. So again, halogen is very good for its color rendering, and so use it in art exhibits. LEDs are improving, but not yet replacing halogen. So you can research the different distributions there and see halogen on the bottom left, and filtered daylight, nice, even, relatively speaking, even distribution, and then what LEDs are getting close to. And there's quite a variety of LEDs that you can get, different quality. Then you want to be able to understand what you're looking at on the label on the box. So you're just shopping in Lowe's or Home Depot or wherever, or you're, as an architect or engineer, specifying these things. You should understand all the different things, the energy efficiency, as well as the lighting qualities. So we want to talk about two things here, efficiency and efficacy. So first we're going to speak of just efficiency, which is somewhat intuitive, and that's the energy per square foot of the building that you're using. And so these are standards here. And before you do anything at all of any quality, you're going to have a 5 of watts per square foot to get lighting. But then if you're being wise about how you're doing it, and scientific and design-minded, ASHRAE, American Society of Heating, Refrigerating, and Air Conditioners, has a standard of 1.2. LEED, we know of LEED is a 0.9, and then 0.5 is the maximum possible that you could get during the day if with daylighting is used. And now we see these percentages down below here. Sunlight through clear glass, and how much is lost as heat. So we have a pie chart, heat versus actual light. And so you want to think about this. We'll think about this in efficacy too, when we're going to speak of in a minute. And then sunlight through spectrally selective low E kind of glass, and then you're going to get much more light and much less heat, and that's an ideal thing. And in most places, you may want to let the heat in the wintertime. So it depends again where you are and what you want to do. So we want to drill down a little bit now into, and this is now chapter 4 out of the one source textbook here, and most of what this slide is paraphrased somewhere in that chapter mostly. But again, visible light is part of the electromagnetic spectrum, and you can go back and look in photovoltaic lectures on that. Visible light is in a range of wavelengths directly related to our temperature of our sun, because that's where we're the star that we're or our planet's orbiting around. Visible light versus thermal radiation, so that's the trade-off. And so you want to see the thermodynamic trade-off of that, and you go in that lecture in thermodynamics. And then you want to speak of the thermal range of the range of thermal radiation, because when we do infrared spectral thermal imaging, and we want to understand the R values of the envelope of the buildings, which we'll discuss later, you want to look for the heat. And so everything's giving off somewhat heat, but including in the visible range, but it peaks quite a bit in the infrared, as you can see on this graph. Now, there's details here you want to come back and look at, but this is a comparison and some terminology you definitely want to memorize. Of lumens is the rate the source emits, and the flux, the efficacy now, not efficiency, but this is lumens per watts. And so you can see that. Now, there's similar pie graphs here of light versus heat for incandescent, fluorescent, and then you see some other comments you should come back and take a look at, and some problems with fluorescence and how to solve that. And then comparing high pressure sodium, halogens, ceramic metal halide, and their efficacies, and LEDs and where we're at. Also, you want to consider the life of all these devices. The LEDs are super high lifetime. It's coming down in cost now too, and a wide range of efficacies depending on how much you spend, and great control over light quality. And you can read about some maximums possible here and how the human brain works a little bit. I have reading at the end of this whole lecture that you can go and read a little more about that. Also, light distribution. So this sometimes written right on the box, and certainly in the spec sheets from the manufacturers. If you're using Revit, you can get this out of the BIM, Building Information Modeling, from the manufacturer, and Suites catalogs and other places. And so you can see how the light's going to distribute. Some other terminology you need to learn as architects, engineers, certainly as illumination engineering consultants if you're going to do that. I did a little bit of illumination design in a consulting firm in San Francisco, but it was secondary to what we were doing on the building, and I would not call myself an expert in this field, although I have quite a bit of education related to it. Illumination, and I've taught this stuff too. So illumination, illuminance per foot candle, lux. So light incident on a unit area, right? Especially for task lighting. If you're working, or you're cooking, or you're reading, or building a model, working in a factory with your hands and their machinery. And then we have brightness versus luminance. Again, this is something you want to read a little bit more about, further reading at the end of the chapter, about how the human brain works and what we see. So luminance is via light meter or your eye, versus brightness, which is perceived. It's a function of the eye's adaptation and the psychology of it. You want to design for both. And luminance needed is a function of task, eye performance, psychology, contrast needed. And then you have very specific task foot candles needed. And to reduce glare, you want to use diffusers, lenses on the fixtures, lampshades, walls, and ceiling, colors and textures. There's also a brightness ratio you should be concerned with, and that's the contrast between adjacent spaces. You can see it, it's analogous to lighting ratio in photography or film production, where you can see the girl's face is not lit up on the far right evenly, on the far left it is, and then I put a picture myself where I do a similar thing, zooming near the window with the sunlight on me, which I know it's doing that. I kind of like the effect, actually. And then finally here, before we go into further reading, just consider the energy use and production overall. And so lighting technologies, due to great innovations in the United States and elsewhere, is now not as much of a contributor to the electrical load. It's still a big contributor. And you can see now sustainable, renewable energy consumption. Hopefully we can do better than that. And we certainly can do much better than this. You're looking here now at you look at the graph, all solar compared to and this is our production, compared to at the top here all fuels. So we're still burning coal and we're still burning oil, and that needs to be changed. You say, oh, we only could do so well. Well, okay. Here's another developed country. Look at what Germany's doing, where it's at in energy use, first of all, consumption, and how they have really dedicated themselves to solar as well as wind offshore. I didn't realize until I looked at this graph that was that big. I knew they'd been to Germany and Austria a couple times, and so I know the dedication they have. And I work with a German company. I'm actually a U.S. representative for, or was the first for the EdgeNet Phoenix Contact. German production, right? Sustainables, renewables. And just look at how much they've done. And this is a very recent graph. Again, Germany. So it doesn't mean we're not doing things here. This is we have electrical load balancing, and power companies have different rate structures, the rates of dollars that they charge you based on a number of things. There's a whole power factor thing I talk about in other lectures of where you have real and reactive power, and how you can put a bank of parallel capacitors in a factory to compensate for bad power factor due to the inductive loads of all the motors. That's a whole different thing. But we're talking about the loads here of actually on peak demand. You tax the grid and the generation, so there's it's bad for the grid, and actually you get a penalty for using electricity during peak times. And so this next thing we look at, Sustainax, founded by one of my students in 2004. And this is what he did. Had 100 employees at one time. Got a picture of him. Hillary Clinton actually went and visited him. And the idea is you compress air during the non-peak times and then release it and generate electricity with that, and the net effect is a cost savings. So you can see more about him and this lecture and more about previous things students have done with me. He actually raised $100,000 for the first robot that we had in international competition. Then when he went and got his master's and PhD, and then raised $12 million in venture capital, and had actually 200 employees at one time. And so supplemental reading, you can learn first about lead points. Go in there and take a look at all that and what credits you get. And then stuff on from the illumination engineering handbook on vision, eyes and brain, the physiology, and then non-visual effects and performance perception. And then related things in high tech, human versus computer vision, how our eyes actually work and our brain too, in addition to what you learn above about the brain, and then the physics display technology and computer graphics cards. Now again, this whole lecture went through very fast. This would be definitely 2 lectures, maybe more. You want to look at all the videos, drill down, take a time, and understand everything. I would say you should spend at least 3 hours on this lecture.